Hello friends, welcome to Mu Lessons. So this is the second part of our basic video, that is the vector calculus. So just going to the triple product or the area of calculating the parallelepiped and curl and divergence, these are the main topics that will be covered in this video. Just I want to give you a review about what we have learned previously in the vector calculus. We have seen about the vector product, how A cross B is made, the formula, the applications part, and what actually A cross B mean in real life. So we have discussed about the magnitude, its direction, its resultant vector, how they are perpendicular to each other. Now the direction was given by right hand thumb rule. Now if we have also talked about the geometrical interpretations in our previous video. There were some properties that were discussed about this vector product. You can find how the vectors are parallel to each other. So there are some of these techniques. So these were the basic things or basic things coverage in our last video. The determinant form was also told, also discussed for calculating the vector product, and we have given you some examples in physics like that of the torque, the angular momentum, and the force in the magnetic field, or the force on a charged particle when it moves on a magnetic field. Then we have tried to solve some examples on how to find this cross product, and we have also got the result. So today we will start with the main topic, that is about the triple product. Now scalar triple product means A dot B cross C, and vector triple product means there will be all cross signs, that is A cross B cross C. So how can you find this scalar triple product? You know how to calculate dot product, and you know how to calculate the cross product. So first calculate the cross product, get a resultant vector, then dot product with the initial one. And how to calculate the cross product you have already seen in the previous video. So in that way you can find how to calculate the cross products by the matrix method. Now what does this scalar triple product say? This says the area of a parallelepiped, means in the previous slides of vector calculus, that is about the cross product of two vectors A cross B or I into J. Those were about the two dimensions. In this case we will discuss about the three dimensional, that means three vectors. What is the geometrical interpretation of this vector? This is the basic reason of discussing this slide. So if you calculate the triple product of three vectors A, B and C, that basically shows the area of a parallelepiped. Now in this case also we will travel in the same manner. Suppose we are having two vectors B and C, and the area will be given as BC sin theta. This is the area of the base. Now we have three vectors B cross C, the resultant is B cross C, and again we have another vector, that is A, and this A makes an angle alpha. So we get A dot B cross C, and this is the net result of the scalar triple product, A dot B cross C cos alpha. And this is nothing but it has a very important geometric interpretation, that is it gives the volume of a parallelepiped. Now here also we'll talk about some properties like interchanging any two rows reverses the sign of the determinant. So A dot B cross C is equals to minus A dot C cross B, and interchanging the two rows twice the original is restored. That means A dot B cross C is equals to B dot C cross A, and that is similar to or equals to C dot A cross B. Now if we will come up with some more properties, that if any two vectors of the scalar triple product are equal, then the scalar triple product is 0. For vector triple product we find A cross B cross C. It can otherwise be written as B into A dot C minus C into A dot B. So better to remember it as back minus cab rule. Generally it is remembered in this manner, so you can make some other rules of your own to make it handy. Now what we sum up from this, that is a physical quantity which has both magnitude and direction, is represented by a vector. It has a geometrical representation, that is, it gives the volume of a parallel pipette. Now we have discussed about the scalar products with vectors. So how to find the scalar product? A dot B means A1B1 plus A2B2 plus A3B3. A cross B is A2B3 minus A3B2 I cap, A3B1 minus A1B3 I cap, and A1B2 minus A2B1 K cap. Scalar triple product, gives the volume of the parallel pipette A dot B cross C. Vector triple product, A cross B cross C by back minus cab rule, and this is also called the quadruple product of the vectors. Now we'll talk about gradient. What is gradient? Gradient is given by this del operator. Gradient means a small change with respect to length, a small change of any value with respect to the length. That is the physical interpretation of gradient. So in mathematics it is given as I into d by dx, dou by dou x plus j into dou by dou y plus k into dou by dou z. Now force will be given as this symbol del operator, we will come to know about it, into F for 3 axes x, y and z simultaneously. So this force will be given as force per unit per unit length, means this gradient value gives the force per unit length in all the 3 axes. I into dou f by dou x plus j into dou f by dou y plus k into dou f by dou z. Now this f is a scalar quantity, that is f is gradient of scalar quantity is a vector quantity. Got clear? That is, the gradient of a scalar quantity gives a vector quantity. Now if you want to make a scalar into a vector, then just take the gradient. Now what is the geometrical interpretation about this gradient? Now when we have talked that it can make a scalar quantity into a vector quantity, so finally we get that gradient is a vector quantity and it will have the magnitude and direction. So df will be delta into f into dl, that is delta f dl cos theta. For fixed value of this magnitude of dl, df is greatest whenever cos theta is 0. That is, we move in the same direction of dou f. That is, no angle difference between dou f and dou l. In that case, it will have the greatest value, because cos 0 is 1 in this case, so that's why. Now the gradient delta f points in the direction of maximum increase of the function. So these are most important things to remember. The magnitude of this delta f or nabla f gives the slope, that is the rate of increase along the maximal direction. Now I'll talk about the divergence. This is the gradient part. Delta f equals to I dou by dou x plus j dou by dou y plus k dou by dou z. Now this operator del operator into f will give dou f by dou fx by dou x, dou fy plus dou y plus dou fs by dou z. In this part we are taking f as a vector quantity, so we'll get f as fx I cap, fx j cap and fx k cap. But when you calculate this divergence, we will do the dot product of this del operator into the vector quantity, and it is a scalar quantity. In case of gradient, we are multiplying this del operator with a scalar when getting a vector. In case of divergence, we are multiplying that same del operator with a vector quantity and we are getting a scalar quantity in case of divergence. So delta dot f is known as the divergence of a vector quantity. Now it has also physical significance, that it represents how much the vector spreads out, diverges from the point. It diverges out, any vector is positive when it shows spreading out of it, and if negative then coming towards that point. So this is one of the important physical significance about divergence. Now you can see we have already seen in these types of structures in physics, in electrostatics. So this point works as a source from which all the elements are going out, and this point works as a saying from which all the elements are getting in. That is, this shows the direction of the divergence of current density. These elements are nothing but the current elements, so this shows the divergence of current density. So J point gives the point amount of charge flowing out per second per unit volume from a small closed surface surrounding that point. Now when these elements are coming out, then we can say this divergence is positive. When it is going inside, it is negative. So if divergence is 0, that is the flux entering any element of the space is exactly balanced by that is leaving that surface. So whenever the amount of entering and amount of leaving remains constant, then we get the divergence to be 0. And such vectors are known as the sinusoidal vectors. Similarly, we will talk about the curl. Curl is the cross product of delta into a vector f. So at this stage, you could be knowing why we were studying cross product, dot product in our previous slides. So this is the main advantage or main usage in curl, divergence and gradient. We'll find the cross product of nabla into a vector quantity. In this case, the vector quantity is given as f. So similarly, now delta cross f is a vector quantity known as the curl of f, and the physical significance is it is a measure of how much the vector curls around that point. So you can see from this picture, it is nothing but the measure of how much of particular vector is getting curled around a particular point. Now there are some second derivatives like the gradient, divergence and the curl are only the first derivative we can make with del operator or the nabla. This is otherwise known as nabla. By applying nabla twice, we can construct 5 species of second derivatives. So these are some example of second derivatives, like the gradient is a vector, so we can take the divergence and curl of it. Obviously this gradient is a vector as we have seen previously, so we can take the divergence first and then curl it. So nabla dot nabla a will be nabla square a. This is the divergence of gradient. Please try to remember all these points. Now what I am saying, these are very important. The curl of a gradient, that is nabla cross nabla into a, is always 0. The divergence is a scalar, so we can take its gradient. Once again I repeat, the divergence is a scalar, so we can take its gradient. Finding the gradient of divergence as nabla whole into nabla dot a. The curl is a vector, so we can take its divergence and curl. Divergence of a curl and the curl of a curl. Divergence of a curl is given as nabla dot a cross b is 0. You can also see from the second point, that is curl of a gradient and divergence of a curl, both results into 0. Now curl of a curl is nabla cross a cap is equals to nabla cross a vector minus nabla square a. So these are very much important points. These 5 points or the 5 formulas you need to remember. There are so many theorems coming out from these points: Stokes theorem, Green's theorem. These are some application of this part. So we will see those things in our next video according to the level of vector calculus as we proceed. So I suggest you to remember all these formulas and just do not mug it up. Try to understand what actually is happening in these cases. Now here is some question. 2 questions I have given for the practice purpose. So you can go through these 2 questions. You can find the answers are also given. So I hope you liked this video, and further we are going to provide some more video on this vector calculus, and that will be more on numerical approach. But one thing I want to suggest is you need to practice a lot for this. Thank you.